potential A and from that, the magnetic field, or to directly calculate the magnetic field. So this basically, we had an interlude, served as background that explained to us what the relationships are. But now we actually want to calculate the magnetic field, and we want to calculate the magnetic forces. And to do that, usually we don't use the relativistic approach. All go. Well, not all. Let me keep remove those parts. I'll leave that out. Okay, so what did we know about the four-vector potential? It's related to the four current. And in the time-independent case, right, so time-independent, this reduces in the in normal space into del squared a sub x equals minus 4 pi over c j sub x. And this is the local current density. Yes?
Is that x as in like,
That's as in
Just
the Cartesian coordinate x.
so what happened to y and z?
Oh, same for all three components. All of the spatial components obey this. Yes?
I'm guessing the minus sign popped out of combining those two.
Yeah, it came from the definitions of the four potentials and the four currents. That a minus sign slipped in there.
Brian's gonna hate this.
Right. From this, since the this vector potential x, the Laplacian, not the Laplacian, but that's the Laplacian.
Yeah.
Of the vector potential component ax yields that, right? We can integrate, and the result is that the vector potential as a function of position in real space, right, is 1 over c, the integral of the current density over wherever the current density is. Right, the thing that links this R to where the currents are is this difference here, right? So the vector potential arises from current that we measure over here arises from current that's over there. And we can also write that since we know we defined that V is equal to curl of the real space vector potential, right? That then from that, V of R is 1 over c, the integral of the R space curl since the only R in here is that, I can pull the J of R out, right? And, or rather, curl of J of R prime is 0. Right? I guess I'll write it like that. That this, equal 1 over c, the integral of J, there should be a minus sign appearing here. Oh, I know where it came from. gradient. dV prime. Then actually taking the gradient. So we have two ways of calculating the magnetic field. One is to directly calculate the vector potential, and sometimes that will be straightforward. And the other way is to directly calculate the magnetic field. We can, now this is an integral over volume, so it's going to turn out that we can use Stokes' theorem in order to simplify this somewhat. But I'm going to hold off on the simplification until after we do a couple of cases where we're just going to bull our way through and do the integral. Then after that, we're going to use some tricks to come up with what is called Ampere's law, right? But I consider, I'm not sure about Ohanian, I think he considers it the other way around. I consider Biot-Savart to be the equivalent basic formula, fundamental formula, to Coulomb's law. The Biot-Savart, law of Biot-Savart, gives you the magnetic field that is created by a charge moving along, and then everything else is just integrating over lots of charges moving in various ways, right? Sometimes the integral is not so easy, but everything else just sort of follows. It's just arithmetic from there, right? And Ampere's law is a simplification which allows for the calculation of the magnetic field under very symmetric conditions. All right. So what I'm going to do now are actually, and I haven't done much of this, examples. Let's see. I'll keep this for now. Okay, so there's actually going to be, I'll come to you, Ryan, don't worry. We're going to go through 4 paths to finding the magnetic field. One of them is the direct integration of current and to find the magnetic potential, vector potential, and then taking the curl of the vector potential, right? 2 is the direct integration of the current to find the magnetic field using this formula here. 3, we'll derive Ampere's law and apply Ampere's law in a couple of cases. And then the thing that I just erased here was a Laplacian for the vector potential, relating it to the currents. And so in a current-free region, the Laplacian of each of the components of the vector potential is 0 if there's no current on this side, which means that we can define actually what's called a scalar potential and deduce that from the solutions to the Laplacian. And the solutions to the Laplacian here are exactly the same as the solutions that we had for the electric potential. What we need then are the boundary conditions. And in magnetics, the boundary conditions are more painful than the boundary conditions in electrics, right? But you are now completely comfortable with expanding the solutions in Cartesian, cylindrical, polar, and spherical coordinates. So you know what the solutions look like. It's just a matter of matching boundary conditions. Okay? So I think I said I was going to use 4 approaches, and I don't know whether I just listed 4.
You listed 4.
We can test later. Okay? So, but we're going to set the Laplacian approach aside for now, and we're going to work on the direct calculations.
I hate series and matching boundary conditions.
So let me start with a calculation from the vector potential. Brian? Oh, yeah.
The equation you
Yeah.
just erased, is that Biot-Savar's law, or is Biot-Savar's law only the one-dimensional one?
That was Biot-Savart law. What do you mean by one-dimensional?
So the one where you treat it only as a one-dimensional wire. Does that, because does that one have a name? The three-dimensional one have a
So
name?
Biot-Savart is this law. The integral over the prime space of the current density in the prime space crossed into r minus r prime over r minus r prime cubed dv prime plus whatever constants I need out front times whatever constants I need out front. I forgot what they were. C?
1 over C.
1 over C. Okay. That is the law of Biot-Savart. The whole thing integrated over 3 space. Okay. What you're accustomed to was that you were finding in physics 2, for example, that this is mu0 over, I think over 4 pi, I don't really remember. Right? Mu0 over 4 pi q v cross r hat over r squared was the way that it was written. Okay? And this is just the sum of this over all possible currents, all the charges in the problem. Okay? So they are both the law of Biot-Savart. I like to express this one actually first because this one looks a lot like Coulomb's law. And I guess then in CGS, this is going to look like.
Is that your back or the chalkboard?
That was my nails.
Oh.
Okay, that explains the screech.
All right, so where was I?
Your nails.
I think it's just
CGS.
a
That's
1
the
over
concept.
C in here that would put it in CGS. Okay. Was that your question, Ryan?
So yeah, it was just the book, and this book had just referred to one-dimensional as Biot-Savart. I was just wondering.
Now the whole thing. I mean, it's actually a good, it's, let's say, a relevant historical question, because I don't know how Biot and Savart conceived it, right? I do know that they did it, this is totally irrelevant. They did it very quickly. That is that Ørsted, how many of you have heard this story? Ørsted, okay. The relationship between currents and magnetic fields was discovered by Ørsted during his undergraduate physics lecture. So he was preparing and giving a lecture, and back then, as now, when you give a big lecture, you want to have demonstrations. So he was going to, from what I understand, fry a wire with, this is about 1820. He was going to fry a wire by having he had a big battery pile, because they didn't actually know how to generate electric power from rotating solenoids, from rotating coils at the time, because that theory and the whole concept had not been developed. So they didn't know that. They just discovered a bunch of stuff about electric currents. And he was just going to fry a wire, show it down and demonstrate Ohm's law. And he was going to do another demonstration that had to do with magnetic fields. So he had a compass nearby, and when he switched the switch, he noticed that the compass reacted. And that was the discovery of the magnetic fields from currents. So he actually did it during class lecture. Information didn't travel very rapidly during that time. It had to be sort of carried from place to place. So it took about 3 months for the information that experiment had occurred to diffuse from Norway to, might have been Denmark, I'm not sure, to the rest of Europe. And Ampere, when Ampere thought about it, within a couple of months, he came up with Ampere's law from the Olmsted experiment, and B.O. Savart came up with their law. B.O.N. Savart came up with their law from hearing about the Ampere from the Ørsted experiment.
Olmsted.
Olmsted, that's local history, from the Ørsted experiment. And they really were in a race. It was like, who did this first? Who gets it out to the rest of the world first? Luckily, in that case, it wasn't the French versus the Germans. It was French versus French. But it was really, this fundamental theory came out within months of the initial discovery. All right.
Would have been funny if it's French versus Germans.
So let me do an example that has a problem in it, actually. There's something problematic about it. What? Of course. Using the vector potential. So we'll set this aside later when we need it. But we'll use the vector potential approach now. So the case that I want to try is an infinitely long wire carrying current. All right, so let's say that it carries a current density of J of R prime, because the wire could be considered to be finite, right? But what I'm going to do is do that integral first, right? But I want to write the whole thing. So we start here, right? And this is a volume integral. And let's do the integral in polar coordinates. And what is that going to give me? Probably a 2 pi r, no r yet. Sorry. Yes, r. dr, no phi, no 2 pi yet. dr
Sine theta r squared dRd.
dz.
Oh,
I need one more. That's what I was.
r primes, I assume?
All primes. Okay. The current is completely symmetric in phi, so I could just go ahead and do that integral. Yeah, I can just go ahead and do the phi integral. It's independent of phi. So I got a 2 pi out here. One down. Okay. The integral in R, actually what we need to do is look at here. What this really is I delta R prime. If it's an infinitesimal line, then
And
the
if it's a
integral, the volume integral over this, yes?
And we're assuming it's a constant current?
Yes. What goes in goes out. That's one of the fundamental laws of physics too. What goes in, it seems to be with respect to learning too. As far as the students, what the students come in with, they go out with. And that's about it.
But we're assuming
But,
like
okay.
negligible
So,
resistance or whatever.
Yeah, we're assuming that the current is constant along the wire, and that the wire is very, very long. All right? So that means that the integral in R can be done. I'm a little bit troubled by my R prime that I've got there. But I'm going to ignore it.
Well, if you define your R of the wire to be at the center of the coordinate system, then you lose the R at the bottom, on the top.
seem to have lost a vector in here.
So J, so you,
Ah, yes. The current here had a direction. It was embedded in J. The current is flowing along the Z direction. So actually, I'm just going to put here and make it clear that that's the current density that we're talking about there. And then to write this explicitly, that's 2 pi over C I integral, oh, I can take the Z hat out, 1 over square root of R squared plus Z squared, Z prime, R prime, dZ prime. That's the integral that we have to do. I actually seem to have gained a factor of 2 pi that I don't want when I look at Ohanian's solution. And so I'm going to strike it. Probably there was a 1 over 2 pi that needed to be in the original expression.
So because we're physicists, we can just adjust the constants as needed.
you already know the ends of the derivation.
I'm
Start
cheating. What?
proof by
In the-
exhaustion.
Are you looking at the book and is there a 2 pi there?
I haven't gotten to that part. There is no 2 pi there.
Okay. This integral,
Boy.
actually, those of you who have done homework in this class have grown to know and love this integral.
You get a 2 pi thing.
No.
Oh, what to strangle it?
And this is going to yield logarithm, okay?
Huh?
Log of z. But our problem is that if that wire is infinitely long, then this is going to go from minus infinity to infinity, and I'm going to be evaluating the logarithm at minus infinity and infinity. And that's not good. So what I'm going to do is cheat a little bit. I'm going to actually say, let's do this, and this is impossible. Well, it's not really. It's okay. Let's do this for a wire of finite length. And how can it be possible? What I could do is say I want to determine the magnetic field at that point, some distance out from the center of the wire. So I'm going to do it at the center because ultimately I'm going to make this wire infinite in extent. And I'll let it go from plus L over 2 to minus L over 2 in Z, right? And then what I could do is have my wires that lead in and out of this go like that. Because the cross product was one that was going to tell us that the magnetic field due to this wire out at that point is going to be 0, right? And let me see where that comes in the vector potential. But I know the magnetic field due to this wire, as long as this wire points at that one, will be 0 at that point along the direction of the current, right? So I can construct a physical situation where I have a wire of finite length and I'm going to calculate the magnetic field due to that wire of finite length. Then I'm just going to let the wire get very, very long and figure out what's going on, okay? Now, actually remember the vector potential here is not the physically measurable quantity. We measure the force due to the interaction of a charge with the magnetic field, not with the vector potential. It turns out that the vector potential actually does have some meaning later on when we get into quantum mechanics and you are using potentials in order to calculate wave functions. But let's do this integral now from minus L over 2 to L over 2. And then we'll just let L get big. And that's the same. And we're going to do this because we don't like the minus in there. 1 over C I Z hat times the twice the integral from 0 to L over 2. Okay? Doesn't matter if it's okay or not, that's what we're going to do. And that's 2I over C Z hat
Excuse me,
minus
Professor?
natural log, yes. of
Uh,
R
That
plus-
square root was originally like an r minus r prime. Where did the r go? Because I just see r primes and z primes.
How the book.
Oh, I'm sorry. Yeah, I should have, okay. Let me go off to this side to make it a little bit easier. I did a rather rapid conversion there, right? That is r minus r prime. What we need to know is what's the distance to a certain element of wire. So there's a distance z prime from the center,
Mm-hmm.
right? So the wire is over there. This is r. If I measure it from this point here, it's actually this distance here. This is what I call r. Not the vector r, but the distance r from the center,
Yeah.
all right? And this here is r squared plus z prime squared, right? And if I'm measuring with respect to this point here, I can call that 0 and measure there, is r prime.
Mm-hmm.
So that's how this turns into that. This is a distance. It's not the vector,
Okay.
okay? Yes? All right.
Yes.
Where was I? Log of L plus square root of r squared plus L squared. Oh, wait. I may have lost a factor of 2,
How did you lose a factor of 2? You added a factor.
because the limit there is L over 2.
You multiplied by 2.
Yes, that's okay. I'm worried about what I actually plugged in here. All right? So I think everywhere an L appears here, I've got an L over 2.
I mean, what you had originally, what you have without the L over 2 is the correct. Because
That's L over 4,
of the
or L squared
his
over 4.
derivation has
He
no,
does it L to minus L.
and then
He
he
does?
does 0.
Or does he do it from
He,
L over 2?
he gets to 0 to L.
And because that's the integral, you can just take the 2 out.
Yeah, but it's not twice. If I went from minus L over 2 to plus L over 2, that's twice the integral from 0 to L over 2.
But he does minus L to L.
Oh, does he?
Yeah, and
That's where you got
Okay,
that form.
then, well, I'm just gonna go back here because of what I've done here and write it like that. Doesn't matter, actually. Because what we're going to do is, where we go like this, right, is that when L gets really, 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 really big, right, then you think, oh, we should ignore that, right? But no, because this is a potential that we're going to take the derivative of. We need to keep the lowest order in R that's going to appear in this equation, and that's that one there, right? But when L gets really, really, really big, this dominates this part over here. And when it's really, really, really big, this becomes a really, really, really big constant. It's really big, but it's a constant. Almost. So this is an approximation. But it will turn out that when we take a look at this case using Ampere's law, that this turns out to be a very good approximation.
Is the constant 0?
No,
It's very large.
this is a really, 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 really big constant. All right? That infinite length of wire contributes to the magnetic potential the vector potential from everywhere, and it does not go away. It's there, right? But it's constant when